All right, so far we have been talking about 5 layer. Now we move on to higher layers. And the advantage of having known the 5 layer is now that we will be using all that knowledge for all the protocols that we will talk about. And the first and most common protocol in wireless is Wi-Fi. In fact, if you pick up any book on wireless networking, it might be 100% on Wi-Fi. For us, it is just 2 lectures, this and the next. Actually, lecture and a half, because we might be moving on to the next item after that. So this one is about wireless LANs, local area networks, and we will talk about basically what we call 802.11 and its features, MAC and physical layers. So it is more popularly known as Wi-Fi. So what is the difference between Wi-Fi and 802.11? So all the local area networking standards are done by IEEE. All right, and IEEE started in this business of local area networking standards. They might be doing some other standards before, but they started on the local area networks in 1980, and I was involved at that time. 1980, February was the first meeting, and so some people say that the committee that was formed for local area network is called 82. Okay, and so there are 802.3, 4, 5, 6, 7, starting from 1, I think we are now to 22, 23, something like that. 802.11, anyone knows what is 802.3? Ethernet, right? So 11 is the wireless local area network, LAN. 15 is personal area network, PAN. 16 is metropolitan area, wireless metropolitan area networks, MAN. So we'll talk about 11, 15, and 16 for sure, and then more. So 11 is the 802.11 is the one that we are going to talk about today. And so this is about local area networks. But the problem with the IEEE standards is that when they come out, they are a combination of ideas from everybody who proposed anything. So somebody says, well, I want to go this direction left, and somebody says, I want to go to right. They say, okay, all right. The standards will allow both left and right. All right. If some people went left and some people went right, after the standard is approved by IEEE, they sit down, form another group, which is called the industry group, and then they decide forever, whether we are going to do both left and right, or just left, or just right. We can't, basically let the customer hang on to, matching left and right? So that is Wi-Fi. Wi-Fi is an industry group called Wireless Fidelity. Fidelity is basically stands for compatibility, wireless compatibility. So Wireless Fidelity is not IEEE. It's a different group where companies go, and I, for example, cannot go to Wi-Fi meeting. I can go to IEEE meeting. IEEE meetings are open. Anybody can go. But Wi-Fi is a membership and so on and so forth industry group. Anyway, so Wi-Fi group sits down and then they decide what part of the features will be implemented. Right? So if you find an equipment which is labeled Wi-Fi, that is guaranteed to work with another equipment which is labeled Wi-Fi. Unless Wi-Fi is is a compatibility label. If you buy 2 Wi-Fi equipments from 2 different manufacturers, they will work. If you buy 2 different things labeled 802.11, they may not work, right? But actually, there is no such thing as labeled 802.11. But what happens is the label Wi-Fi will be there. That means it is industry standard. So everybody understands the difference between 11 and Wi-Fi? Any question about that? All right. So when the 11 was being developed at that time, we had other standards such as HyperLAN in Europe, and there were many proprietary networks at that time. Now they're all gone now. Once Wi-Fi came in, everybody started using Wi-Fi, even here as well as in Europe, everywhere. So now Wi-Fi is the standard, and we will talk about. So we will interchangeably use Wi-Fi and 11 during this presentation. But most of the lecture is actually about 11. There is not much here that is specific to Wi-Fi. So with that, we will just now not use. We will just mostly concentrate on 11. What is in the standards? So now the 11 itself was done around 1997-98. So about 13 years ago. At that time, it ran at 1 and 2 megabits. And obviously, as soon as the standard came out, it was obsolete because nobody wanted to use 1 and 2 megabits. Right? 97, who will want 1 megabit or 2 megabits? So, by the way, we had 10 megabit Ethernet in 1980. So 20 years later, if somebody comes up with a standard which is 1 megabit, that was just considered too low. So right away, they started working on a higher speed standard, and they call them A and B, 82.11a and 82.11b. So the newer versions now are, we have G, N, and they run at 1154, 108, 200, and so on and so forth. Very high speed, up to 200 megabits. And we will talk about how they do that. Now they support both ad hoc and base stations. So base station based is more common, so you have an access point. We don't call them base stations for 11, by the way. We call them access points. So we have an access point, and then you connect to the access point, a central point, right? Ad hoc means you connect from one computer to the next. Okay, so if you have two computers, two laptops, both have Wi-Fi in them, you can connect them directly. You don't need an access point. Suppose you're in a hotel or in a meeting or on the road, and you want to transfer a file from one computer to the next, you don't need a wireless base station or access point. You can just directly connect them. For example, most commonly we use it for reaching out to our iPhone or something else which has Wi-Fi in it. If you have another device that has Wi-Fi in it, you can connect them by point to point, and that is called ad hoc mode. How many of you have used ad hoc mode? Nobody has used ad hoc mode? All right. How many of you have iPhones? Okay. All right. That's all right. It's not something, but the reason is I'm asking that is because iPhone is redefining the whole wireless LAN. Wireless LAN. For the first time, I myself used ad hoc mode when I got my Wi-Fi and my iPhone, right? Because it just, leading edge in some sense, right? And so that's why I asked. Now, so that's the only time I use ad hoc mode. I've never used ad hoc mode before that, all right? And it's like Bluetooth. Sometimes in Bluetooth, it's always ad hoc mode. In Bluetooth, when you want to connect two devices, you just connect them point to point. You don't need an access point. Right, so Bluetooth is always ad hoc mode. Wi-Fi allows you ad hoc mode, but we don't use it very often. The way you recognize ad hoc mode is how? How do you find out if some network is running in ad hoc mode? Anybody knows that? So when you go to your computer and you say, show me all the wireless LANs, have you done that? You can say, show me all the wireless LAN. If it shows a tower or something, that's an access point. If it shows you another computer, that is another computer, basically. That's an ad hoc mode. And oftentimes, and this is interesting, you go to the airport, you turn on your laptop, see what is available to you. You will find lots of computers available to you to connect. In fact, if you do that inside the plane, you will find lots of computers ready to connect to you because those guys have not turned off their Wi-Fi. You have not turned off, that is wrong, but they have not turned off either. Actually, by the way, this is another topic to go and talk about whether it is okay to turn on the Wi-Fi in plane. That's the whole discussion that wireless guys have, but not today. So the idea is, and some of these computers will be labeled as public Wi-Fi, as if they are. So some people who don't know much about this thing can connect to them, and you can do a lot of. They can do a lot of damage to you. And so, this is one of the projects we do in the security class. Actually, we are not going to do in this class, but in the security class, we did a project where somebody set up a network like that to catch all the key information. So security is a key issue, right? So one thing is that, so ad hoc mode, so much about ad hoc mode, and then the base station mode, right? So that is, we also call it infrastructure based. When we say infrastructure based, that means the access points and the base stations. Without the infrastructure, we have ad hoc mode. And 802.11 uses spread spectrum. Now, anybody remembers what is spread spectrum? Yeah?
That's where you're broadcasting on a bunch of different frequencies.
So one method is frequency hopping. You randomly select the frequency, transmit to that one, and then randomly change to another one and transmit to that one, and so on and so forth. That is one spectrum. There was another method. Second method is, there are two methods of spread spectrum.
Just designate a specific band that each user would use?
No, a specific code. So everybody has a different code, and instead of sending one bit, you send 10 chips or 20 chips or 100 chips, we call them. So basically, instead of sending one, you send 10, 10, 10. So you have a code, and that distinguishes you from other people that have a different code. So that is, both of them, that is called direct sequence. So 11 uses both direct sequence and frequency hopping. Okay. So 11 uses both direct sequence and frequency hopping. It runs at 915 megahertz, 2.4 gigahertz, 5 gigahertz, and 850 nanometers. So what are those things? So it is unlicensed. Unlicensed means that you don't need to get a license to operate. Most of the other wireless devices, the spectrum has to be licensed before you can use them. And the reason they have to be licensed is so that no two people will use it at the same time, right, and causing trouble to each other. But in the case of three bands, 915, 900 megahertz, 2.4 gigahertz, and 5 gigahertz, these are unlicensed. Actually, we should not call them unlicensed. We should call them license exempt. These are three license exempt bands where anybody can transmit. And the way you protect yourself is by following some rules, which is what we'll talk about here, media access control. In addition, Wi-Fi also runs with a light, and that light is infrared, diffused infrared, and that light is 850 to 900 nanometer. So we talked about this also in the phi layer, that the light comes in different colors, and infrared is where? Anybody remember? Infrared is just below the red. Right? So if you remember the spectrum of light, the infrared is just below the red, and that is what we use in remote controls, for example. At home, when you press on a remote control, a red light comes out. And same thing is, so initially, most computers used to have the infrared in the back, and you could connect two computers using infrared. In fact, we used to connect a computer and a printer using infrared. Now those are gone. Now in the days of Bluetooth, infrared is gone and Bluetooth has taken over. But infrared was used for short distances. So we have these three modes. Actually, even that is not very much used. 915 is not very much used. 2.4 is the one that is used everywhere because this is worldwide. So the problem with the spectrum is it is available in some countries and not available in the other countries. And therefore, 2.4 gigahertz is most common one, which is worldwide. The next one is 5 gigahertz. And however, we don't use it that much even now because it's just that it may not be available at some places. Second thing is that 2.4 gigahertz actually is just common. It's just very congested right now. So everything that you do wirelessly at home, whether it is Wi-Fi or whether you are doing telephony, cardless telephone, or whether you're doing and many remote controls and so on and so forth, they all work using 2.4 gigahertz. So it's very congested. It supports multiple priorities and time critical in data traffic. So basically you could have voice traffic going at the same time. Having said that, this is 11 which supports it. Most of the implementations don't have that mode. And then the power management allows a node to doze off. That is supported. So basically power management is one where if you have a wireless device, it can go to sleep and not lose anything. And we will talk about how that happens. All right. So now we look at the channels. So there are two bands which are used, 2.4 gigahertz and 5 gigahertz. 2.4 gigahertz has 12 channels. Has 12 channels. I don't see channel number 12 here, but basically the channels are like this. Channel 1 goes from this frequency here to here, 20 megahertz. Channel 2 goes from somewhere here to here, and channel 3 goes there. So they are overlapping. All right. So channel 12 must be going from somewhere here to the end. The point is that these channels are overlapping. If somebody is operating channel 1 and somebody is operating channel 2, they will certainly collide. They will not collide in the sense that they will cause noise or confusion or interfere with each other. So the only three channels which are not overlapping are 1, 6 and 11. Actually you could also have 3, 7 and something, right? But since we can't remember all those numbers, only thing we remember, all of us, now that you are a Wi-Fi engineer, wireless engineer, you would remember is channel 1, 6 and 11. Those are the three non-overlapping channels. You set your computer, your access point to either 1, 6 or 11. Make sense? There are 12 channels, but we just use 3. Why? Because we can't really use overlapping channels, and those are the simplest one to remember and to use. And if you use channel 1 and if you find a lot of interference from your neighbor, you switch to channel 6. If you find some interference, then go to channel 11. All right. In the 5 gigahertz band, there are a lot more channels. All of them are still 20 megahertz. However, there are lots of channels. The number goes all the way to 161, as you can see here. Out of them, only 12 are non-overlapping, which are shown here. However, we cannot remember these numbers. So far, we don't generally use 5 gigahertz. Second thing, we can't even remember. So I can't just tell you that, okay, well, change to 6 or 11 or something like that. But these are the channels, again, 20 gigahertz channels that are used there. The key thing to remember is that the channels are 20 megahertz, not gigahertz, 20 megahertz each. And second thing, this 1, 6 and 11 is kind of a common knowledge nowadays for people who are working in Wi-Fi. Other things we don't, we just have to look up. All right, so little bit more detail about 11. The first part was 11 itself, which ran at 1 and 2 and ran only at 2.4 gigahertz and infrared. The second one was A and B, which were issued in 99, and B ran at 11 megabits using 2.4 gigahertz. And this you have to remember, because some of this thing people have to know common sense. So we know that B runs at 2.4 and A runs at 5 gigahertz band, and it gives you 54 megabits. All right, well, B gives you only 11. So the secret to 54 is OFDM. Now, anybody remembers what is OFDM? Huh? Frequency division multiplex. What was O? Orthogonal, right? So So OFDM is what gives it 5 times more for the same spectrum. Okay. However, when A came out, it was working in 5 gigahertz band, and people just didn't like that. So they said, we can't really use 5 gigahertz band. Let's use another standard which runs at 2.4 gigahertz but has OFDM. So then we had to design G, 802.11g, which came out in 2003, and it also gives you 54 megabits on the same 20 megahertz. The only difference is it gives you at 2.4 gigahertz. And the last one actually, which is not on this slide, I should probably say fifth part, is 11N. It just came out 2000, I think it is 9. It came out just last year, or it may not have come out. I have to double check that one. But anyway, so it came out last year, and that runs at twice the speed of this. Twice the 54 is 108. And that secret is MIMO. So it gives you twice the data rate by using multiple antennas. All right. So much about physical layer and physical layer and physical layer. So now let's move on to the higher layer. One of the problems with the wireless is that you cannot really use CSMA-CD. CSMA-CD, if you remember, in 473 is carrier sense multiple access with collision detection. And so if I transmit and somebody else transmits, we can hear each other and we can say we collided, and then we back off. Right? You cannot do that in wireless because you can collide but not hear. And this is what happens. Suppose C is transmitting to B and A is transmitting to B. B can hear both of them, but A cannot hear C and C cannot hear A. So when A transmits, the transmission goes through and A does not hear any problem, and it says, okay, all right, I must have gone through. And similarly the C, but they may not have gone through because they must have collided at B and the B didn't get anything. Right? So this is called hidden node problem. C is hidden for A and A is hidden for C. So a hidden node might be transmitting and you cannot hear them, but they will be colliding with your transmission. All right? And so the only person who can hear both is B, the receiver. So the receiver has to tell you that I got it, I didn't get it, that somebody collided or didn't collide. And therefore, we cannot use CSMA-CD. We have to do something different, where after you have transmitted, you wait for the receiver to tell you that it has received it. So there is a mandatory acknowledgement of every packet. At the link layer. All right? So that's what we do. Rather than finding out after I transmitted 1500 bytes that I lost the packet, what we do is we just send a small packet first, 5 byte packet, actually not 5 byte, I don't know the size, very small packet, which is simply a message says, hey, I want to talk, ready to send. And everybody says, whoever wants to transmit says, I am ready to send, and they might collide. If they don't collide, if they succeed, then the receiver will say, all right, you can send, clear to send. And everybody will hear that this particular station has been allowed to send. And not only that, it will say, I'm ready to send 1500 bytes, and that will say, you are clear to send 1500 bytes. So everybody knows that now for next 1500 bytes, we have to wait for this station to go. Then that station will send that 1500 bytes, and it will get the acknowledgement. After that, we start the whole cycle again. So for every packet, we have to send 4 packets. This is called 4-way handshake. First we get the permission to send, then we send the packet, and then we get the acknowledgement. Why is it required? Because
Nodes can prevent
yeah, hidden node problem. All right, and this is called CSMA-CA, Carrier Sense Multiple Access with Collision Avoidance. So what is CSMA? Before you say that I want to send, you first listen. Is anybody already transmitting? Suppose you just came on and you want to send, you just don't send. You just first listen, carrier sense. If nobody is saying anything, nobody is transmitting, then you send RTS. All right, so that is the part, CSMA, CA. RTS is the CA part, collision avoidance part. CSMA is that first part where you listen before you can even transmit RTS. Listen before you talk. If the medium is busy, the transmitter backs off for a random period. A avoids collision by sending a short message ready to send. RTS contains the destination address and duration of message. So that was ready to send. That message contains the address where I want to send to and the duration of the message. Tells everyone to back off for that duration. All right? And then the destination sends clear to send. By the way, when I say destination here, there are two modes. In the infrastructure mode, what is the destination? It's always either the access point or the station. All right? You always talk to the access point or the access point talks to you. You don't talk A to B. If you talk A to B directly, that is called ad hoc mode. All right? So that is the destination. So the destination clear to send, and other stations set their network allocation vector nav to not transmit for that duration. So they keep a register called nav which says, okay, stop for 5 milliseconds. Actually not 5 milliseconds, whatever time that maximum packet size is. Or the packet size is, whatever size you set here. For that much time, you just have to wait. Cannot detect collisions, and therefore each packet is AGGed, and MAC level retransmission if not AGGed. Now what happens if you don't get the acknowledgement? You retransmit the whole packet all over again. Retransmit means you start from the beginning. You say, I want to send, get the clear to send the packet, and then wait for the acknowledgement all over again. And therefore, before you start sending, you have to wait and see that the medium is idle, but then the wait time is very different for different people. And these wait times are three kinds. First is called short interframe spacing. Second one is called medium, but it is called PIFs, point coordination interframe spacing, and third one is the larger one is called diffs, and that is the distributed interframe spacing. So CIF is a very small time. If you have something very high priority, you look, you sense the medium and you say, well, nobody is talking and I have high priority stuff, so therefore I will send, but you have to wait CIF time before you can send, right? If you don't have high priority, then you have to wait for diff. Diff is longer period. So if you have lower priority stuff, you wait. If the medium is idle for that long, then you can go ahead. It's quite possible that while you are waiting, somebody else comes along because they have a higher priority message. They will wait CIF and they will transmit. All right, so this is how we do priorities. Now what is PIFs about? Then there is one mode which is pre-allocated mode, where you could say, well, I want to send some voice or something which every 5 milliseconds I want to send 10 bytes. This is time critical. And so we'll allocate that amount for every time, and then you don't have to go through RTS, CTS, stuff. And those people have to wait for PIFs. if they can, if the PIFs is available, after that they go on a pre-scheduled period. In that one they will be told that, well, you can send 1 millisecond, you can send 2 milliseconds, you can send 3 milliseconds. So that period will be done. However, PIFs are not implemented. So this is more of a theory. And I will talk more about the PIFs here in this slide. In this slide, basically, first the whole thing starts with a beacon. So beacon is a frame that the access point sends out and says, look, this is Wustel. What is the name of Wustel SSID? Boofy. This is Boofy S or Boofy, and so it announces that so that you know that Boofy is available here, right? And so that is in the beacon. After the beacon, and there are a few other things in the beacon, by the way, we'll talk about that also in a minute. But after the beacon, then people can send CIFs and diffs and PIFs. If you have PIFs, then there is a period reserved for contention free. So that is the pre-reserved period, during which whatever reservation you have, whoever has the reservation can talk for that long. After that period is over, then people will basically do the normal contention based stuff, which is what we do. All right. So this is for time critical messages, this is for time not critical messages, and this beacon is what starts the whole cycle all over again. And so the super frame actually is fixed duration, and so base station or the access point will every so many milliseconds will transmit the beacon and say, okay, all right, here's the situation, I'm still up. And in fact, there is other thing in the beacon which says that to stations number 3, you were sleeping, I have some packet for you. So every station will probably wake up at that particular time to listen to the beacon and then go back to sleep. Alright, so beacon serves many purposes, including starting a new frame, announcing the SSID, and telling the sleeping nodes that they have a packet. Okay, so now question is, to everyone it is clear what are the 3 interfacing spaces for interframe spaces for? But a CIF is used for sending the acknowledgement, and so when you send an RTS, within one CIF you will get the CTS. When you send the packet, within one CIF you will get the acknowledgement. Okay, so those are the highest priority thing. If somebody send a packet, they are not going to wait for a random time to get the acknowledgement. Acknowledgement has to come immediately following the packet. All right. Now, if you send a RTS, let's say, and you collide, to another person sends the RTS, what do? Well, you could just wait another some time, maybe diffs, and then send it again, and then again collide, and then send it again and again collide. So instead of doing that, what you do is you wait for a longer period than just the diffs. And every time you collide, you increase that period by a factor of 2. I mean, not the waiting period, but the randomness. So what you do is we keep something called contention window, and first time we draw a random number between 0 and the contention window, and whatever number comes out, that is how long we wait. When we collide, then we increase the contention window by a factor of 2. So the contention window becomes 2CW and plus 1 or CW max. So it never goes below minimum something and never goes above maximum something. So the contention window has a minimum and the maximum, and every time you collide, you go up by a factor of 2 approximately by following this formula, 2CW plus 1. Once you have a new CW, you draw a random number between 0 and CW. So suppose your CW is 15. So you draw a random number between 0 and 15, and the random number comes out 7 for you. Then you just wait for 7 diffs before you can send your what packet? What packet? RTS. Your packets never collide, by the way. Why not? Why your packets don't collide? Because you got the prior permission. Because if your RTS went through, everybody heard your CTS, then nobody will, hopefully in a good mood, or the correct mood, or the working mood, will collide. But RTS can collide. Right? So this whole contention window applies for RTS. And so when you send the RTS, if you get the CTS, fine. If you don't get the CTS, then you draw a random number, wait that longer, and yeah, go ahead. Question? Have a question?
If you're not on the network and you connect while someone else is transmitting, can you send an RTS out without?
No. So when you're not on the network, when you come in, first thing you do is look for the beacon. All right? And the beacon will tell you what is CIFS, diffs, PIFs value. And so you have to do that. Right? So basically you have to join the network. And so you cannot just come and start transmitting. That answers your question? Okay. All right. So the contention window doubles every time, but it is just the range which doubles, not the number. The number will be random. So if there are two people who collided, one will draw a number 7, one will draw a number 5, and the number 5 will get through. Right? And the 7 one will, when it comes, what will it see? It comes back after 7, it sees the medium is busy. So it just doesn't start transmitting at 7, it goes and senses the medium at 7. Alright? So the next time you sense is this random number. This random number tells you how long you wait before you sense again, not transmit again. And this is important to understand because this is in the homework today and this is in the exam also, every time. Alright? So you understand this clearly, okay? Let's show you a little more detail. So what are the typical parameter values? The CIF is about 10 microsecond. Congestion window goes from 31 to 1023, and all these numbers are here. For frequency hopping phi, it was CIF was 28 microsecond, and for 11A, 16 microsecond, for 11B, 10 microseconds. You are not supposed to remember any of this, but you're just supposed to know that these are all different for different networks. And you get all this from the beacon. And PIFs is CIF plus 1 slot time, and diffs is CIF plus 2 slot time, and the slot times are given here. 9 microsecond, 50 microsecond, 20 microsecond, and so on and so forth. And all of these numbers obviously are based upon some simulations people did and figured out that at those speeds, at those kind of workloads, and so on and so forth, those are the right numbers. Okay? So here's an example, and that please listen carefully. This is what I said is in the homework and in the exam. So we have a slot time of 1 unit. CW min is 5, diffs is 3, PIFs is 2, and CIFs is 1. If I just told you that the CIFs is 1 and the slot time is 1, then you should be able to figure out PIFs and diffs. Right? I just told you that the PIFs is 1 plus slot time plus CIFs, and these 2 slot times plus CIFs. Right? So anyway. So now station 1 sent a frame. Right? While station 1 was sending the frame, station 2 started and wanted to send a frame at this time. What will it have to do? It says that the medium is busy, right? So it says I will wait until the medium becomes free. When the medium becomes free, it has to wait how long? How many units of time? It diffs, right? And diffs is 3 units of time. So it will wait 1, 2, and 3 here. Sorry. So it waits. So this is the CIF, this is the acknowledgement, and then it has to wait 3 units of time after that. And then once it waits there, it goes and it checks whether the medium is available. All right. Actually, what it does is it draws a random number between 0 and 5. A random number between 0 and 5. 5 is the congestion window, and its random number comes out to some number, and then at that point it goes and sees if the medium is still available, and since the medium is available, it starts transmitting. So there are several waits here. First, when the thing goes away, it waits for the acknowledgement will come here. After that, it will wait. This acknowledgement will go through, because if the frame was going from station 1 to station 4, the station 4 will send the acknowledgement back, and then the 2 will start. After that goes away, it will start the diffs wait. After diffs wait, it will start the congestion window wait, and then the medium is still available, then it sends it. All right. Similarly, here the station 3 comes on. Sorry, actually I have to change that one. That is not a transmission. Anyway, station 3 comes on at the same time, and it finds the station busy. It does the same amount of wait. Here it draws a random number. The number for the station 3 comes out lower than station 2. So actually the station 3 is the one that is transmitting, not the station 2. All right. And station 4 also wants to send. Station 4 comes here and draws the random number, and it finds that the medium is busy, so the station 3 gets through. Now what is happening is that the station 2 has started its timer. This is the nav part we were talking about, that the station 2 waited for the diffs, drew a random number, and then said, okay, I am going to wait that long before I sense the medium. It is waiting that long, and then it finds the medium busy. Right? This one drew, and it found that that long, and it finds the medium is busy. So they start their cycle all over again. Yeah.
I'm not sure why in the station 4 at slot 45 has a backup signal.
Station?
Yeah, in the station 4,
Uh-huh.
for the slots 4 to 5, there is a signal for backup, right?
The here?
No, before this.
This one?
Yeah.
That's the acknowledgement.
Yeah, but actually the diagram you said like the black makes the backup signal, right?
This is okay. So let me clarify. The frame is shown by a red dot in my slide. You cannot see the red dots, but it says frame in there, right? The hatched blue hatch is while they are backing off, right? And this is actually a red dot here, but I couldn't write the word ACK, so I wrote the ACK on the top. But this is actually the ACK frame.
So what you mean is in station 4, 3, and 2, even they don't transmit the frame, they also will have transmit the SIFs and get it.
Okay, all right. Let me just again start. Station 1 was transmitting when this station wanted to start transmitting. So these up arrows are indicating when they have the frame ready to send. They just want to send. Before that, they had no desire to send. They were sleeping or they didn't have anything to send. They were idle. But at this time, station 2 wants to send. It's just desire. It's not transmitting. It just desires to transmit.
But it still has some safes and acknowledgement in station 2 and 4.
Now, so what it does is, it goes, first thing when you want to transmit, what do you do? Suppose you want to ask a question, right? What do? You wait until I stop speaking. I come to a full period or something, I stop a little bit, right? End of a sentence. You just don't start speaking in the middle, right? Same thing here. So it wants to transmit, but it sees that the medium is busy. So it doesn't start any timer at that point.
Yeah.
It waits until the medium is free.
Yeah, I know the frame will be transmitted after the medium is free, but I'm not sure. The safes and acknowledgement is still, drawn in the station 2, 3, and 4. So I'm not sure what you mean.
Yeah. Okay. Yeah. No. Let me see. The
There's a pre-allocated time common for everybody, right? Safes and acknowledgement time. So
safes and acknowledgement time is fixed, and acknowledgement time, by the way, is exactly one slot. The questions he's asking is that how would the station 2 know that we have to wait these 2 periods?
they synchronize the clock, right?
Huh?
They synchronize their clock all the time.
I have a question in my own mind, so I am not sure. I have to double check that. See, the idea is because every frame is followed by an ACK. So, clearly station 2 knows that this will be followed by an ACK. So that is there. But the question I have in my mind is, if you came in the middle of the ACK, how would you know that this is an ACK? Right? And so there won't be any other ACK after this. Is that the question you're asking?
Almost.
Okay, something similar. So, but if we know that this is a frame, then we know that we have to wait for 2 slot times, because we have to wait for safes and we have to wait for the ACK, and then we have to wait after this is medium is really becoming free here. So the medium really becomes free here, and then we draw our we have to wait for diffs or whatever congestion window we waited for diffs actually, and then we found the medium is still free. Now we draw our congestion window. Once we draw the congestion window, then we have to basically wait that long, and out of these 3 stations, this one drew the random number which came out how much? Now let's see. So the first station number 2, the random number came out to 3. Okay. For station 4, the random number came out to 2. And for station 3, the random number came out to 1. Alright, so they waited that long and then went back. So when 3 came back at 1 period, it found that the medium is still available and it started transmitting. Basically, that frame actually is probably an RTS. Alright? And then when this thing came out, then it finds it busy, and then finds it busy, and so on and so forth. So there is a little bit more detail about how to distinguish between an ACK and a frame. Actually, there's a little bit more detail here, and that is that while they're waiting here, they monitor the frame they monitor the media, and so it says I have to wait for 3 units of time, and it finishes 1 unit and somebody comes in. At that time it stops waiting and says, well, I will wait 2 more units of time later on. And so what it does is it comes back here. Now it just waits for that long, 2 more units of time it has to wait. But what happens is after 1 unit of time the media becomes busy again. So then it says I have to wait for 1 more unit of time left over. So there is one more detail which I didn't say so far, is that basically once you draw the random number, which was in this case 3, you complete that much wait, you allow the media to be free that much time. So you first waited 1 unit here, another unit here, and then you wait 1 more unit here before 2 can transmit. Station number 3 just luckily draw random number 1, so it was able to transmit and there is no problem. Station number 4 drew the number 2, so it transmitted for 1 unit of time, and then it stopped its, that is what we call NAV, the NAV timer, NAV. And then it started the timer again when after waiting for the diffs period, and then it became, the media was still free, so then it started transmitting. So this 1 unit of time is same as this 1 unit of time. This 2 unit of time actually is just 1 here, and then plus 1 will be somewhere else, which is not shown in this slide. So let's just recap this thing, and this is important to understand, is that after the previous transmission ends, the ACK ends. In both cases, the ACK is part of the frame. So you see a frame, you wait for the shifts, and you get the ACK. So that much is just part of the frame. So this frame and this ACK are actually one and the same in some sense, right? So after that is done, then you wait for diffs, and then you restart your NAV. If NAV is 0, you draw a new number, but if NAV is not 0, you just restart that NAV. So here at this point everybody's NAV is 0. We don't have another one? Okay, then we have to locate where that is, but anyway, right here. Page 3 is in the bag. Anyway, all right. So I think this answers your first question too, is that frames are always followed by the ACK. So you don't have to know that. If you find something busy, then they will be followed by the ACK. And then if you came in the middle of the ACK, then basically they will be free for diffs period of time, so you will know that your diff is done. Anyway, so you wait for the diffs, and then you restart your NAV. And if the NAV is 0, then you draw a random number between whatever the congestion window is. And here the NAV is 0 for all 3, and so the first station number 3 draws the number 1, station number 4 draws the number 2, station number 2 draws the number 3, and they start waiting while still monitoring the medium. Right? So now the station 3 comes on, and so the station 2 and 4 stop their NAV. I'm coming to your question. So they stop their NAV, means they just now know that they have to still wait more. And they will wait until the next diff comes around, and that time they will restart their NAV, because the NAV is non-zero. They will restart their NAV, and then they will start waiting. Now the station 4 will win this time, and then station 2 will stop its NAV when the station 4 wins, and they will continue after that. All right? Okay, now your question.
So on your next slide, you describe how this is happening. And in T4 it says station 1 receives ACK for its transmission.
Yeah?
But I mean, for one, I guess I don't see that frame coming in, and then the next one, there's another act that comes for station 4. So I guess that was a bit confusing.
Where is another racket?
Well, so on the time 4, station 1 receives an act, and that's the.
That is coming from 4.
I'm sorry?
That is coming from 4, the same act. At t equal to 4, station 4 sends an act to station 1.
Okay, so 1 and 4 are communicating. Okay.
Okay? Alright. So I think now everything should be clear. Basically, every time you get a frame, the act is following. After the act, you wait for the diffs. And after the diffs, you wait for your nav. If your nav is 0, then you draw a random number. If not, then you continue your previous nav until the medium becomes busy. Alright, a little bit more complicated than necessary, but that is what it is right now. Okay? And being in the wireless class, you should be able to just draw these diagrams. And so one of the exercises for today is to draw this diagram. Do you feel comfortable enough to be able to draw this? Okay. All right. So then we have already finished this slide. That finishes the end of this. Is finishes of this part. And so the 5 things in this part are, first of all, it uses frequency hopping and direct sequence both. It also uses CDMA. Well, both of them are CDMA. It also uses OFDM. So which one uses OFDM? Anybody remembers now? So we have A, we have 11 without any letter. Then we have A, B, G, and N. What does A add? How does A?
It uses DM, so it's G, right?
Huh?
A and G.
A and G both use, actually A, G, and N all use OFDM. B doesn't use OFDM, so B runs at 11. Now A and G both use OFDM, and that's why they get how much? 54. Now G runs at 2.4, whereas A runs at 5. Then we got N, which runs at both 2.4 and 5, but it gives you twice the rate of A and G. By how? By MIMO. Okay. Then the 11 PHYs are A, B, and G and N. Allows both ad hoc and infrastructure most. So these 2 points actually we have not covered, but this point BSS, which is next slide in a minute, we are going to cover that one. And here is that 802.11 supports single FIFO queue versus and uses SIFs, PIFs, and DIFs. So basically we understand SIFs, PIFs, and DIFs. The idea here, single FIFO queue, is that basically the packets which they come in, they just stand in the queue and first in, first out inside the station. Okay, so the homework 6. Homework 6 is 2 802.11 stations get the frame to transmit at t equal to 0. The third station has just finished transmitting a long packet at t equal to 0. The transmission parameters are slot time, shifts, and diffs, which are exactly the same as before. CW min is 5. CW max is 7. Assume that the pseudo number generators generated are 1 and 3. Alright, so already given random numbers generated so that everybody gets the same result. The frame size is 3 slots. Draw a transition diagram. How many slots before the 2 packets will get acknowledged, assuming no new arrivals? Yeah.
Random numbers are generated. Are they generated for, like, in what order? The first one is 1, and the second one is 3.
Yeah.
Okay.
So basically, since there is station number 1, 2, and 3, station 1 will generate a random number which says it's got 1. Then station number 2 will generate a random number which says it got 3.
And then 1 and 3, 1 and 3.
No, that's it. That's all you need. You only need.
Oh, yeah, because those
This is it. The whole for this problem you only need 2.
Right.
I still have a question
Yeah.
diagram. I saw the second frame is like has the time slots, like 4 time slots, but the first frame is only 3 time slots. I mean, in the
First frame is 3 time slots. Second frame is 9 through 12. So 9, 10, 11,
no, I think it's
12, 13. Yeah.
9 to 13.
Yeah, 4 slots. Yeah, 9,
Yeah.
4 slots, and the third frame is whatever. Yeah.
So, I mean, the second frame is, why the second frame is 4 is something related to the.
So we have to give it to, no, we have to tell you what the frame size is, because the frame sizes are not fixed.
Okay.
I mean, you might want to send whatever you want to send, so the frame size is what you want to send.
So there's nothing related to the confidential window size?
No. See, there is, basically you don't want to send a very long frame, because if you send a very long frame, the chances of errors are very high. The error rate on the wireless is 10 raised to minus 3. So if you send something 1000 bits, and you might get 1 bit in error, and then the whole thing is, I mean, actually the whole thing is not bad. You will have some other methods to protect you, but you don't want to send too long a packet. All right, so the key here is to understand diffs, CIFs, and PIFs, and to understand CSMS, and basically this CA thing, that there's RTS, CTS. And what we have not done actually in this timing diagram, and you are not doing in your timing diagram, is, which is actually not right, is, but we're going to stick with it, is we didn't show RTS, CTS. So we should be showing RTS, CTS, and that will just extend the timing a little bit more. All right, so I'm going to move on to the next chapter, unless there are any questions about this homework. Okay, so please give the next handout while I switch.